Hello, everyone, and welcome back to part two of this two-part series on chapter four of flight physiology and human factors. And in this chapter, we are examining the life cycle of oxygen in the human body, breathing mechanisms, and the main thing that we're looking at in this chapter is the relationship between the altitude that you attain in your aircraft and what that does to your body, specifically what it does to your body's ability to obtain oxygen for your cells, and hypoxia, which is among many other things, one of the gravest risks to your health and ability to pilot your aircraft safely during your flight operations if something were to go wrong. So, in part one, we examined the composition of the atmosphere in terms of gases like nitrogen and oxygen. We looked at the mechanics of breathing, and we looked at the three kinds of respiration, which are external, internal, and cellular respiration, which basically tells the story for how your body obtains air that is rich in oxygen from the environment, how your body moves that oxygen from the air into your blood, how your body carries that oxygen in the blood, and then how your body delivers that oxygen to cells in the body and how they utilize that for the energy they need to function. So in part two now that we've discussed all that, and you can see here we had just wrapped up a discussion on hemoglobin and how hemoglobin responds to the different partial pressures of oxygen that are logarithmically related to your altitude that you've attained. In part two, we are going to start looking at the actual downstream physiological consequences of attaining high altitude but not having supplemental oxygen or not having a cabin pressurization mechanism. So we are going to be focusing on hypoxia here. So hypoxia refers to the deficiency of oxygen in the blood, tissues, and cells. There is a horrible, horrible typo here, so please forgive me for that. So for the blood, tissues, and cells, that is sufficient to cause physiological dysfunction. So we want to make sure that we are being clear this is a deficiency of oxygen. Hypoxia does not imply that there is no oxygen present at all. So that would be what we call anoxia. That is distinct from hypoxia. So hypoxia is different in the sense that your body and your cells are still obtaining oxygen. They're just not obtaining enough to really function at full capacity. So what we're going to kind of see here as we move through this part of the chapter is that hypoxia, while it does have a very quick and insidious onset, the effects of hypoxia are not instantaneous, whereas the effects of anoxia, we can speculate, would be almost instantaneous. So up until this point, we have learned, and if you're not recalling some of this, you can go back to the part one of this video series on chapter four. Up until this point, we have learned that there are many different stages in the oxygen life cycle in the body. So external, internal, and cellular respiration, and we can also include the transport of oxygen in the blood by hemoglobin in there. So if we're talking about hypoxia, which ultimately is the cells and the tissues not receiving enough oxygen, there can be a number of different reasons why a cell or why a tissue or why an organ like the brain is not receiving enough oxygen. And we can relate that to potential problems at any point in the life cycle of oxygen, whether, again, it's external, internal, or cellular respiration. So we can disrupt the ability of the body to use oxygen for a variety of different reasons, and that's going to ultimately lead to our discussion on the four different types of hypoxia. So the four different types of hypoxia are, number one, hypoxic hypoxia, which if you're like me, that has always sounded to me like it's kind of a redundant thing. It sounds like that was a term that was coined by the Department of Redundancy Department. So hypoxic hypoxia is also referred to as altitude hypoxia. So as a pilot or as a future pilot, this is going to be the kind of hypoxia that you are 99% of the time going to be concerned with. So this is the kind of hypoxia that is the result of being at a high altitude, so being above 10,000 feet in altitude and not having supplemental oxygen to breathe. So you can see here that this table kind of localizes the impediment here to be the lungs. So as we learned in the previous video, at high altitude, the total air pressure is much lower, and that consequently causes there to be a much lower partial pressure of oxygen due to what we learned with Dalton's law. So ultimately, when you are breathing at high altitude, you are not obtaining enough oxygen through the lungs. But of course, that is going to lead to downstream consequences of there not being enough oxygen in the blood, there not being enough oxygen in the tissues. So ultimately, there's not enough oxygen in hypoxic hypoxia at multiple places along the life cycle of oxygen, but the actual location of the defect or impediment is in the lungs. So we're going to spend most of our time talking about hypoxic hypoxia, but we will spend a little bit of time talking about the other types, which are hypemic hypoxia, which usually is going to refer to either someone being anemic or being poisoned with carbon monoxide. So we will talk about that in just a little bit. So the location of the impediment here is the blood. So what that would indicate is that a person is breathing an adequate amount of oxygen-rich air. There's just a defect in the blood and the ability of hemoglobin to actually carry that oxygen once it's in the bloodstream. We'll talk about stagnant hypoxia, which refers to usually issues with the actual cardiovascular system. So either an issue with the heart being able to adequately pump the blood throughout the body and get that oxygen to the tissues, a problem with maybe something like atherosclerosis or an infarction, which would cause a heart attack or stroke. So in this case, we're talking about a problem with actually pumping the blood. We're not talking about a problem with breathing. We're not talking about a problem with the actual ability of hemoglobin to carry oxygen. We're talking about the ability of the cardiovascular system to pump blood. So that is stagnant hypoxia. And then finally, there is histotoxic hypoxia, where the location of the impediment is the cells themselves. So usually this is going to be the result of some kind of outside drug or poison or stimulant or depressant, so alcohol, drugs, narcotics, over-the-counter stuff, anything that can chemically affect the way your cells utilize oxygen in cellular respiration can cause histotoxic hypoxia. So we will have time to talk about all of these as we go along here. So we're going to start with hypoxic hypoxia, which, as I mentioned, is the principal kind of hypoxia that you as a pilot are going to need to be aware of. So as we've said, this type of hypoxia is caused by exposure to the low air pressure at high altitudes, which of course causes a low partial pressure of oxygen, leading to your lungs not being able to obtain enough oxygen via external and internal respiration. And then, as I mentioned, this is going to lead to low amounts of oxygen at every step downstream of that. So that includes oxygen transport by hemoglobin in the blood, and then delivery of oxygen to the cells for the purpose of getting energy through cellular respiration. So there are 4 stages to hypoxic hypoxia, which are called the indifferent stage, the compensatory stage, the disturbance stage, and then finally the critical stage. So as you can kind of imagine, these stages are defined based on the altitude that you are currently at, in terms of whether you're like not in an aircraft at all and you're near sea level, or whether you're at a very high altitude. And it shouldn't be a surprise that the altitude you have attained and the actual effects you are feeling and what stage of hypoxic hypoxia you are in relates very heavily to how much oxygen you are actually carrying in your blood. So if we look at the first stage, the indifferent stage, the reason why this is called indifferent is because you are largely not experiencing any symptoms of hypoxia, and 90 to 98% SpO2 percentage, or oxygen saturation percentage, that is well within the range of normal physiological function. So this is going to be the stage of hypoxia you are in or not in when you are either at sea level or near sea level or below 10,000 feet. And we've said before that anything above 10,000 feet is going to be where you start experiencing the symptoms of hypoxia. So we'll spend some time talking about each of these stages, but we'll also look at the compensatory stage, which shows itself when you climb to above 10,000 feet but below 15,000 feet, and you can see that your oxygen saturation has dropped there. So you can kind of see on the right-hand column that your symptoms are going to get progressively worse and worse and worse with each stage. Climb even higher than 15,000 feet and you'll get into the disturbance stage where your oxygen saturation dips below 80%. You start to have psychomotor controls, motor issues, difficulty handling the operation of the flight controls, problems with cognition, and then finally the critical stage, which is going to show itself when you climb above 20,000 feet. This is the most dangerous aspect of hypoxia because you run the risk of becoming completely incapacitated and unable to pilot your aircraft. If you go back and look at some of the examples that we've looked at of hypoxia, whether it be the 1999 Learjet crash that claimed the life of Payne Stewart, or the Helios Airways flight that is mentioned in Chapter 3 of your textbook, in both of these cases, most everybody on board the airplane was completely unconscious and incapacitated, indicating that they were climbing at a very high altitude and they did not have supplemental oxygen on board. So their oxygen saturation percentages were well below 70%, and they did not have enough oxygen to even stay conscious, let alone operate the flight controls. Okay, so the indifference stage, you're going to be flying at or below 10,000 feet, like we said, and this will cause your SpO2 percentage to drop to no lower than 90%, which really is just barely adequate for normal physiological function. So if you go back and look at that table that we just looked at, really the only symptom that you're going to see is diminished ability to see at night. And the reason is because out of all the tissues in your body, the one that requires oxygen the most is actually the retina of your eye. This is the very back of your eye, and this contains all of the light-sensitive photoreceptor cells that will allow you to see. These cells are under the highest oxygen tension in the whole body. They have the highest demand for oxygen. So these are going to be the cells and tissue in your body that are most sensitive to a decrease in your SpO2 percentage. So it's no surprise that this is going to be the aspect of your physiology that is affected first, is your vision. So some other signs or symptoms of the indifferent stage include euphoria, which is a general feeling of well-being and happiness, and then elevated heart rate and breathing rate. And we will talk about what is indicated by the elevated heart rate and breathing rate when we get to the compensatory stage here in just a minute. But your textbook actually does a pretty good job of telling an anecdotal story about euphoria, in that the actual author of the textbook was actually flying with somebody and they had ascended, I think, to like over 13,000 feet, and both the pilot and the passenger were experiencing the effects of euphoria. They just felt really, really good and really, really happy. And thankfully, both the pilot and the passenger knew what this meant. They knew that this was kind of the indicator that you're in the indifferent stage of hypoxia, and they took that to mean, in spite of their feeling of well-being and happiness, they took that as to mean that they need to descend in altitude, and once they did that, that feeling of euphoria went away pretty quickly. So the compensatory stage, again, this is going to be where you climb above 10,000 feet. So your SpO2 percentage is going to continue to drop. So the way your body is going to respond to a drop in oxygen levels in the blood is your body will attempt to do two things. Your body will attempt to obtain more oxygen to replace the oxygen that is not there, so that explains the increase in breathing rate. You can certainly see the logic there. If there's not enough oxygen in the blood, well, let's breathe more so we can pull more oxygen in. And then your heart rate will go up in an attempt to circulate the oxygen that is in the blood a little bit faster and hasten the delivery of oxygen to the cells. So both of these effects are mediated by what is called your autonomic nervous system, especially the sympathetic branch of the autonomic nervous system. We may get into that a little bit later in the class, but for now, it's just important that you understand the logic of why your heart rate and your breathing rate would go up when your oxygen levels go down. The logic is that we're trying to hasten and quicken the delivery of what little oxygen we do have to the cells that need it. So, in this stage of hypoxia, the body will be able to overcome hypoxia by employing these methods, but only in the short term. This is a good strategy for overcoming the effects of hypoxia when oxygen is running low for a little while, but this is not a permanent solution. This is like putting duct tape on a hole in a septic tank. So maybe it'll get you by for a couple of minutes, but it is not meant to be a permanent solution. So this compensatory stage will hold off things like things that we see in the later stages of hypoxia, but these are stopgap measures. So the NTSB advises pilots to limit their exposure to altitudes this high for no more than 30 minutes because on average, that's about how long the compensatory stage lasts. And that obviously assumes that you're not carrying any onboard oxygen and you don't have a cabin pressurization mechanism. Okay, and then the disturbance and critical stages. So as altitude continues to be gained above 15,000 feet, obviously we saw the SpO2 percentage is going to continue to drop, and the body cannot fully and adequately supply oxygen to the brain in order to support cognitive function, even with your increase in heart rate and increase in breathing rate going the way it is. So that is the disturbance stage. You start to see some of the cognitive and psychomotor effects, the ability to make good decisions, to remember key pieces of information, to operate the flight controls. And then when you get to the critical stage, the loss of oxygen is going to be so severe that consciousness and loss and death will come if something is not done right away. So ultimately, when you're thinking about hypoxia and really any kind of hypoxia, you don't want to forget the true purpose of oxygen in your body is to support the energy production in your cells. Your cells need energy in order to adequately function. So any of the signs or symptoms of hypoxia that we're going to see ultimately relate to the inability of your cells and your tissues and your organs to do their normal jobs because they are not able to make enough energy in order to do those things. So here are some of the signs and symptoms of hypoxia. The difference between a sign and a symptom is that a sign is detectable by others, whereas a symptom is usually only detectable by you yourself, if you are the victim here. So some hypoxia signs are rapid breathing, which obviously we just talked about, cyanosis, which we will see a picture of a little bit later. So this is kind of the blue coloration in the skin, which indicates that hemoglobin is not bound to oxygen. A reduced reaction time, which indicates that, okay, the nervous system is not getting enough energy to send messages properly. A feeling of lethargy, muscle incoordination, impaired judgment, mental confusion, and then in the critical stages, unconsciousness, and then we mentioned euphoria. Euphoria, thankfully, is a sign that is identifiable very early on, and it usually is one of the things you want to look for immediately as a sign that maybe you're starting to experience the signs of hypoxia. And then some symptoms include breathlessness, apprehension, fatigue, nausea, headache, lightheadedness, hot and cold sensation, tingling or numbness, and then visual impairment. Those bottom two, the euphoria and the visual impairment, are the two that you should probably be looking for the most closely because those are going to be the ones that show up the earliest compared to some of the others. So some of the principal physiological signs of hypoxia are cyanosis in the skin. So this picture will kind of show you what that looks like. This person is kind of in the early stages of showing cyanosis. They're only really showing it in their fingertips. If you do a Google image search for cyanosis, you can see some much more severe cases of it. Severe visual impairment, which we indicated is logical because of the way the retina has a much higher oxygen demand than anywhere else in the body. And then poor muscle coordination, which we will learn later in the semester that your ability to contract your muscles, which gives you the motor control you need to operate your flight controls, this is all controlled via your somatic nervous system, which ultimately comes from your cerebral cortex in your brain. So if your brain and if your muscles are not getting enough oxygen, they are not going to have enough energy to do the sorts of very fine coordinated movements that they would normally do. So, the most dangerous aspect of hypoxia is how difficult it is to recognize or self diagnose and how quickly it can sneak up on you. Your textbook calls this hypoxia's insidious onset. So, it's one of those things, like, unless you are looking very carefully for it and unless you are very, very hyper aware of it, you can become severely hypoxic before you really even realize it. So, one of the things your textbook mentions later on in the chapter is that a lot of pilots are encouraged to go through essentially hypoxia training to train themselves to understand what hypoxia feels like. And when pilots choose to do this, they can be subjected to hypobaric chamber tests that can simulate the effects of hypoxia so that a pilot can actually learn to recognize what it feels like and what it looks like when it comes and how quickly it can come. So next what we'll talk about is what's called the time of useful consciousness, which describes the amount of time following a decrease in SpO2 percentage that a pilot actually has to continue and make good sound decisions. So this graph will actually show you another logarithmic relationship between that time of useful consciousness on the y-axis and then the altitude you've ascended to on the x-axis. So the reason why we're not seeing any data at or below 10,000 feet is because you theoretically shouldn't experience any symptoms of hypoxia down there. So once you ascend past 10,000 feet and into 15,000 feet, if you're at 15,000 feet, then your time of useful consciousness at maximum is going to be about 90 minutes. So the numbers in this graph don't really account for individual genetic and physiological differences from one pilot to the next. And then other things like diet and physical activity. So these really should be assumed to be maximum times of useful consciousness rather than minimums or averages. So at about 15,000 feet, you maybe have an hour to an hour and a half to deal with that compensatory stage where you actually are still able to think properly. And ideally, this would be the time when you would try and recognize that you are experiencing the effects of hypoxia and descend to a lower altitude. So you can obviously see that as you gain in altitude, your time of useful consciousness continues to plummet. And when you get to about 25,000 feet, you can really see that insidious and rapid onset of hypoxia starting to rear its ugly head. And then you can see some of these as well. So at 50,000 feet, you literally have 6 seconds. So that is hardly any time to do anything at all. But that 50,000 feet threshold kind of gets back to what we talked about back in chapter 3. Nobody's really going to be flying that high unless you are wearing a pressurization suit. Okay, so let's now talk about hyperventilation. So when hypoxia sets in, one of the autonomic effects that your body will set in is an increased breathing rate in an attempt to compensate for the lack of oxygen. So we want to remember here that breathing serves two purposes: to bring in oxygen and to also expel carbon dioxide. So we kind of hyper-focus on oxygen here, but carbon dioxide is also an important part of this story. So hyperventilation will solve the problem temporarily of bringing in new oxygen. So when we say hyperventilation, we just mean breathing more and breathing more rapidly than you otherwise would need to. So this will actually solve the problem of bringing in new oxygen, but it actually creates a new problem in that you are getting rid of too much carbon dioxide. So the physiology is a little bit complicated and we're not going to completely get into it, but basically what I'll say is that you should have a certain amount of carbon dioxide in your blood at all time. You don't want to completely get rid of carbon dioxide. You don't want to have too much, but you don't want to have too little either. So the reason for this is that carbon dioxide in your blood actually helps to be a major determinant of the pH balance in your blood. The pH of your blood is something that we want to carefully regulate. It should be between 7.35 and 7.45. The pH scale biologically runs from 0 to 14, where 0 is very acidic and 14 is very basic or alkaline. So your blood should be just a little on the basic or alkaline side of the neutrality scale. So the amount of carbon dioxide in the blood actually helps to set the pH levels of the blood plasma, which again should be about 7.4 or so. So the way this works is that carbon dioxide in your blood can combine with water in a chemical reaction that produces carbonic acid. And as an acid, that will decrease the pH of the blood. So this chemical reaction here should be very well balanced if there is a normal amount of carbon dioxide in the blood. With normal ventilation, we are shooting for about 40 millimeters mercury of carbon dioxide as the partial pressure in the blood. If you start breathing too little, which is called hypoventilation, carbon dioxide starts to build up in the blood because you're not getting rid of that carbon dioxide through your normal breathing rhythm. So if carbon dioxide builds up in the blood, then you're going to get even more carbonic acid being formed, and the pH of your blood will get way too low, and that's called acidosis. But with hyperventilation, which is what we're talking about here, if you're breathing too much, then you're getting rid of too much carbon dioxide. Your PCO2 maybe drops to about 20 millimeters mercury, and you get the opposite problem. You're not forming enough carbonic acid, and the absence of the acid will actually shift the pH balance towards the alkaline side, and you'll end up with a pH that's too high, which is called alkalosis. So again, when the body expels too much carbon dioxide, which is called hypocapnia, this causes the blood to become too alkaline, which results in alkalosis. So a shift in the acid-base balance in the blood will actually cause a lot of problems throughout the body. So cells will stop functioning correctly, hemoglobin will not carry oxygen correctly, and you will have a decreased amount of blood flow to the brain, which, again, those are things that sound bad when you're thinking about the things that are necessary to pilot an aircraft successfully. So as you can imagine, these consequences will compound the effects of hypoxia, and in some cases will even mimic them. So I don't want you to think that hyperventilation only occurs when you're dealing with hypoxia. Hyperventilation can come even when you're standing on terra firma at 0 feet above sea level. So things like nervousness, anxiousness can cause you to breathe too fast. And if you breathe too fast, then these sorts of things can happen. So it's important to understand the difference between hypoxia and hyperventilation, but there are cases where they can work together and kind of compound each other's problems. So as a pilot, it's going to be, like I said, the altitude-related hypoxic hypoxia. That's the one that you need to be the most aware of. But let's talk a little bit about some of the other types. You have hypemic hypoxia, which is indicating that the respiratory system is bringing in adequate amounts of oxygen, but the oxygen is not transported well in the blood. So we'll talk about that here in a second. There's stagnant hypoxia, in which we implicate the cardiovascular system as being the problem for not adequately pumping oxygen-rich blood into the tissues. And then you have histotoxic hypoxia, in which the utilization of oxygen by the cells in the body is impaired due to the presence of some sort of chemical that affects those sorts of chemical reactions, things like drugs, alcohol, or poisons. So for hypemic hypoxia, there are two major causes. Number one is anemia, which can refer either to a low blood volume, a low red blood cell count, or a low iron content. And any one of these implies an impairment in the ability of hemoglobin to carry oxygen throughout the body. Or alternatively, you can get hypemic hypoxia through carbon monoxide poisoning. Carbon monoxide can come from all sorts of things like cigarette smoke to engine exhaust or any kind of machine that burns fuel. So carbon monoxide, which again is distinct from carbon dioxide, so please make sure that you don't confuse the two, carbon monoxide exposure will actually cause hemoglobin to unload its oxygen before it actually delivers it to the tissues, which results in the tissues not receiving the oxygen that they need. So the funny thing about carbon monoxide poisoning and hemoglobin is that hemoglobin actually has a much higher preference or affinity for carbon monoxide than it does oxygen. So if your hemoglobin is carrying around all this oxygen and then carbon monoxide shows up, essentially hemoglobin will just drop all of its oxygen so that it has the opportunity to grab onto that carbon monoxide. It seems like a major evolutionary defect in how our bodies are put together, but that's just kind of how it is. So we can actually see the oxygen and carbon monoxide dissociation curves for hemoglobin here. So basically, without getting into the mathematics here, if you see one of these curves that is pushed all the way to the left in the graph, that indicates that you have a very tight and very high affinity between hemoglobin and whatever it is bound. So carbon monoxide, the fact that this graph is all the way to the left indicates that hemoglobin really, really, really likes carbon monoxide and really likes binding to it. And if you're talking about the ability to transport oxygen throughout the body, that's a major problem. We really do not want there to be any carbon monoxide in the blood because that will cause major problems for our ability to carry oxygen around. So if you do experience the effects of carbon monoxide poisoning, the treatment involves breathing 100% oxygen, which is very similar to the treatment for hypoxia. So here you can actually see what are called the physiological altitudes for a given carboxyhemoglobin content in the blood. So that would indicate that like X amount of carbon monoxide that is bound to hemoglobin. So if you have 0% carboxyhemoglobin, indicating that you are not experiencing any of the effects of carbon monoxide poisoning, your physiological altitude should match your actual altitude. So if you are at 6,000 feet, physically your body behaves like it's at 6,000 feet. If you're at 7,000 feet, your body behaves like it's at 7,000 feet. But at 5% carbon monoxide at 6,000 feet, your body behaves like it's above 10,000 feet. And your body at this altitude, like we've said, will start to experience some of the effects of hypoxia. So you can see that that problem gets compounded as you ascend in the atmosphere and as your carbon monoxide content goes up. So this is definitely worth knowing about, especially later when we start talking about the difference between smokers and non-smokers as pilots. And then here we can actually see some of the physiological responses to different carbon monoxide concentrations in the blood. So below 10%, usually you're just having some mild symptoms or usually not many symptoms at all. But as the percentage goes up, some of these symptoms get a little bit worse and worse until eventually you end up with unconsciousness, which you will recognize as being the worst possible outcome of hypoxia. Well, in this case, it's hypemic hypoxia. So it's just a different kind of hypoxia that has a different type of cause. For stagnant hypoxia, we said this is usually going to be a cardiovascular system issue. So the cardiovascular system consists of the pump-like heart, which circulates blood throughout the body, through the arteries, the capillaries, and then the veins back to the heart. So the purpose for pumping this blood is to make sure that the tissues throughout the body, so brain, liver, skeletal muscle, skin, etc., they receive oxygen-rich blood, which that oxygen ultimately came from the air that we breathed. So if some kind of medical episode like a heart attack or stroke impedes the ability of the tissues to receive oxygen, those tissues will very quickly become hypoxic in that they are not receiving enough oxygen. Additionally, pulling positive G's in flight, and we will have a future chapter, I think it's chapter 8, that focuses on the effect of gravitational force on the human body and physiology. Pulling positive G's in flight will also cause some blood flow to slow down and stagnate, which will produce some of the effects of stagnant hypoxia as well. And then histotoxic hypoxia, this is a very specific type of hypoxia. What it implies is that external and internal respiration are working properly and that the oxygen carrying capacity of hemoglobin is normal too. So it's indicating that we are doing a good job of obtaining oxygen from the atmosphere and transporting it through the blood. We're just not using it very well once that oxygen gets to the tissues. So outside contaminants can affect the ability of cells and tissues to use oxygen during cellular respiration. A very good but very extreme example of this is cyanide, which is a poison that inhibits the final step in cellular respiration that produces the energy that we need in order for our cells to function properly. And this is such a potent poison, and it works so well that it is fatal almost immediately. So In that particular case, the effects of histotoxic hypoxia are so severe that you probably wouldn't even have enough time to actually feel them or recognize them. So let's talk about some environmental factors that will compound the risk of hypoxia. So obviously altitude that you've attained is a pretty obvious one, as is the duration at that altitude. So that relates not only to your SpO2 percentage, but also your time of useful consciousness. The rate of ascent and depressurization will also come into play, and your textbook will actually spend some time talking about cabin pressurization mechanisms and the difference between gradual and explosive decompression and how quickly those sorts of things may or may not occur. And then cabin temperature and or humidity can affect things as well. Very humid air will have lower partial pressures of oxygen, so those can exacerbate the effects of hypoxia as well. And then some individual factors can include things like physical fitness and activity, illness, emotional state, whether you're a smoker or not, anemia like we talked about with hypemic hypoxia, and then the presence of alcohol or drugs, which we obviously talked about with histotoxic hypoxia. So what all of these individual factors have in common with each other is that they produce bodily states that imply some sort of increased need for oxygen, which of course is going to put you at higher risk of hypoxia. So you could look at the physical fitness and activity as being part of this. If you give yourself a really heavy workout before you fly up at altitude, you're going to be a lot more sensitive to hypoxia because you have conditioned yourself to need more oxygen because you're using your muscles a lot more. And then for smoking, I'd said that we would mention this. The carbon monoxide that is in cigarette smoke just by itself is not going to be sufficient to cause hypoxia, but it will sensitize you to hypoxia at altitude. So you can see that we're comparing two different kinds of pilots, one that is a smoker and one that it's a non-smoker. The smoker is going to have a higher physiological altitude because of the presence of carbon monoxide in their blood. So if both of these pilots fly to 10,000 feet, then the non-smoker probably won't be experiencing the effects of hypoxia that the smoker will. So as far as preventing hypoxia goes, the obvious answer is, okay, you need to get oxygen, right? So in non-pressurized aircraft, which accounts for most of the general aviation fleet, flying above 10,000 feet requires supplemental oxygen to be carried on board and delivered to the pilot and passengers using a variety of different delivery systems that you can read about on your own in your textbook. And then cabin pressurization, when it's present, not only will prevent hypoxia, but also many of the other physiological drawbacks of flying at high altitude, which we will talk about some of those in the next chapter on trapped and evolved gases. Cabin depressurization is exceedingly rare, but if it does occur, the primary threat to health is still hypoxia. So here is a good summary of some important altitude thresholds that you ought to be aware of and some of the federal regulations that require pilots to either carry supplemental oxygen or how long they should stay at that particular altitude before descending. So I'm not going to go through every single one of these, but you ought to become aware of them if you can. And then just to summarize, this chapter will hopefully have kind of given you an appreciation for what oxygen is, how we obtain it, and why it's so biologically critical to your minute-to-minute physiological function. And hopefully you'll also appreciate the absolute danger that hypoxia poses to your life and to your ability to pilot your airplane safely. So the threat hypoxia poses should really be kind of top of your mind when you're flying above 10,000 feet. And you need to be aware not only of federal regulations, but also risk factors, the nature of how oxygen is delivered to you on your aircraft, and what sorts of signs and symptoms that you need to be aware of in yourself and in the others around you that signal that you may be becoming hypoxic. Okay, well, thank you so much for your attention. That's going to wrap up Chapter 4. Join us next time and we will start talking about Chapter 5, which discusses trapped and evolved gases within the body. See you next time.